Okay, there was a team of us that in 2012 formed ourselves into a team to try to understand and solve the problem of frangipans in Kentucky. Frangipans have been here for thousands of years. We've accepted the fact that they're a inferior soil to a lot of soils we have in Kentucky, and we've learned to live with them. But we wanted to see if we could change that. And these are the number of four. These are the names of the people that were part of the team. This is a picture of a frangipan soil that we dug on the back of the research farm. This is fescue on the top. This is the A horizon of the topsoil. Then below that is the subsoil. And then below that you can see this white streak that comes through there. And that's the frangipan. So this layer here and here, this whole layer, the top and the subsoil are laying on top of the frangipan. This frangipan stops all the rooting. The rooting comes down to the frangipan and it pretty well stops. Water, as it moves through the soil, comes down to the frangipan and pretty well stops. So all that you can raise a crop on is this first 20, in this case, first 20 inches. So we got to raise a crop on 20 inches of soil unless we can solve this problem of dissolving that frangipan. This is an old profile. From the frangipan right here is an old soil profile, and then several thousand years ago this new profile of soil was laying on top of this by wind erosion that came from the Mississippi River Basin and floodplain and blew over the top of this. And it's quite a significant thing, and when it did that, it caused a chemical reaction, and this chemical reaction caused each one of these soil particles in this old profile to cement together. So we have a block of cement of individual particles cemented together below this that prevents roots and prevents water from going through them. If you were to dig down into that profile where the frangipan is and take a sample of it, it would look like this right here. And this reddish areas all in here are all cemented together. These little parts of gray are little small streaks that you can get some water and some rooting. So it's not entirely stops all rooting, doesn't entirely stop all water, but virtually it does that. It's just as if you don't have any rooting and water movement through this part of the profile. So it's a very onerous soil. It's a very difficult one to manage. The winter it gets too wet and it's easy to get stuck. In the summer, because it's so shallow, it gets too dry, and your yields are usually hampered by that. This green right here is the distribution of frangipans in the state of Kentucky. You can see that where the wind blows in from the Mississippi River and from the Ohio River Basin here, that during that time these deposits were made in through here, and that's where we have most of our frangipan problems in the state of Kentucky. Now, this area right here has very few frangipans, and that's because those are limestone soils that occur down in the southern part of Kentucky, and they're well drained, and they were alkaline when this was blown in, so and it weren't acid. You have to have an acid condition to form this frangipan. All these were sandstone soils and were in acid condition. The frangipan itself goes way beyond Kentucky. Here is Kentucky. Here is Louisiana, Arkansas, Missouri, Mississippi, Alabama, Tennessee, southern Indiana, southern Illinois, southern Ohio, Pennsylvania, New York. It's scattered throughout. There's 50 million acres, 50 million acres in the United States. It's a very significant problem in the United States. Now, the part that's cemented together that we showed you down there, that's about 20 inches, 24 inches below the soil profile, but for the top, below the grass, it's 2 to 4 feet thick on the average. It can be 6 feet, it can be 18 inches, but on the average it's 2 to 4 feet thick. So if we can dissolve that 2 to 4 feet thick, then we've got a soil that's not 2 feet deep, but it's 4 feet deep. And that makes a huge difference in the amount of water that can be held and supplied to the crop. It's cemented by aluminum silicates, and that's just a cement that holds it together. And that's what we're trying to dissolve. The average depth of the pan is 20 to 24 inches in the state of Kentucky. It can be as deep as 30, 32, 36 inches. It can be as shallow as 16, 12 inches. But on the average, it's about that deep. And that's not enough water holding capacity to make you a good crop every year. You really need 3, and it's really need 4 feet. 3 is very helpful, but 4 feet is really what you need to protect you against constant threats of drought. So as we talked about before, it stops water movement, it stops root growth, and it limits water holding capacity. On the average, we say it reduces yields about 20-25% over what some of the other soils that we have in the state of Kentucky. Excuse me. So we tried to solve this problem, and we worked in the lab, we worked in the greenhouse, and we worked in the field. We started in the laboratory. We could take these hunks about the size of your fist, take these hunks of the fragipan, the hardest part of the fragipan, and then we could introduce a solution of all kinds of chemicals, all kinds of fertilizers, all kinds of things that the farmers use, and see if it breaks up the fragipan and trying to find something. We also used a lot of the common plants that farmers use, and especially cover crops, to see if any of those had the capacity to break apart and dissolve the fragipan. And this is the way we did it. We took a hunk and put it in here. We introduced that solution. We waited 30 days to see how it fell apart. Here is some of the experiments. We've probably done close to 100 of these different things. We found about 5 different materials that would make a difference. And this is where the fragipan, that clod, the fragipan fell apart really well. So this material right here, which is potassium chloride, dissolved the cement and it fell apart. This one down here is still a clod, still like it was before. There was no dissolution that took place. And so this is the way that we determined if we had found and had a hit on something that would dissolve the fragipan. And so we've done many of these, and we found one plant of all the plants we've tested, and we haven't tested them all, but we found one plant that had the capacity to break apart the fragipan, to dissolve it. And this is what's showing here is ryegrass. These are different varieties of ryegrass, and some is the tops and some is the roots, but of maybe the same variety, but there's several different varieties. And the smaller the number, the lower the bar, that means the smaller the particles, so the better that material was. The higher the bar, the bigger that particle was left over after 30 days, and it wasn't as effective. So the smaller bars. So this shows you how effective that some of the ryegrass varieties were in breaking apart. So that's what we begin to concentrate on. We begin to concentrate on how we can use ryegrass to break apart that fragipan for the farmers of the state of Kentucky and make this soil deeper and more productive. And we're beginning to show signs that it's a real thing, not only in the laboratory, but in the greenhouse as well as the field. Now this is the greenhouse. These are, you can see in the background, all the different types of soil cores that we have introduced, different chemicals, different plants, and we're growing those, and then we watch and we look and we see how the roots are growing. We see how if the soil has changed. In this particular case right here, we have ryegrass. This mark right here was where the fragipan was. This was the topsoil. This was the subsoil. And the fragipan started right here. We have grown ryegrass on this 6 times, 6 different times. And now, instead of seeing a solid fragipan, as I showed you a while ago in that picture, what we have is roots. We have the fragipan beginning to come apart, and we're seeing that the rooting of the ryegrass into the fragipan is successfully breaking parts of it apart. It's a slow process. You don't do it all in one time. It takes many years to do it as you continue to get it downward, but we've really broken it. In this part right here, from this fragipan where it starts down to here, there's parts down here broken, but this is pretty well all effectively broken. So basically, it increases the productivity of this particular core, this particular soil that we have here. We can measure these, and we'll take them apart and measure them. And so we have, as I said, decided that ryegrass is going to be one of our main functions. Now we have data that supports some of this also. Data from the field that shows that we get some increase in ryegrass, some increase of corn and soybean yields grown after ryegrass cover crops. And, but we don't have a lot of years of data. What does it do in the long run? Because I said it was slow breaking it down, and it takes several years. This is a field that we took from Hamilton County, Illinois, where Mr. Junior Upton, working with Mike Plummer, has grown annual ryegrass as a cover crop for 15 years and then grew corn after that. He supplied me with the yields that he had. And the blue line is the difference, and then I took Hamilton County, Illinois, and I averaged for each year that he gave me his yields, I took the average county yields of corn for Hamilton County, Illinois, which is where he is located. And I subtracted the difference between that field and the average fields of Hamilton County, Illinois. So that puts at zero, this line right here, that puts at zero what we're comparing it to. And so the difference between Hamilton County, Illinois yields in 2001 and the difference in his field in 2001 was almost 30 bushels, 27, 28 bushels. And then the next year, at the fourth year, he had 13 bushels above the county average. So you can see that he's starting to climb. So if we take a trend line, we make a trend line, it comes up here and it goes all the way through there. It averages that blue line. And if you compare that trend line to the average yields of the county, you start out 15 bushels below the average. His field on the average yield 15 bushels below. It wound up 40 bushels above the county average. That's a 55 bushel yield increase. Now, this is not scientific. There was no comparison. The comparison was to all the fields in that county. So it's not, I couldn't say it's solid scientific information. And, he had one variety. They had all different types of varieties. We don't know how that compares. We don't know any of that. But it is pretty good evidence that it is really working and really real. And not only is the evidence that's really working really real, it also shows that if we're just half of what this shows and gain, that it's quite a significant change and could make quite a significant difference to the people that farm these soils. So we're continuing to do research. We're going to try and prove scientifically what it is. We're going to try to describe it scientifically as we continue on the research. But we're excited about the possibility of making a significant change in Kentucky as well as in the United States.